You can start, George.
Okay. 1, 2. It's okay. Okay. Hi, everyone. Thanks for joining the talk. It's been a long 2 days. And I'll take my turn to thank the organizers and for this wonderful opportunity and everything. So, but let's start. We will cover 6 topics. We'll start with team. Then we'll move to the inspiration, the idea. Then on to the hardware. Then we're going to talk about neural networks. We're not data scientists, so probably we're not like the ideal candidates to talk about neural networks, but we'll just set the stage. We'll not go into the theory. I mean, probably you heard very good talks during this conference about neural networks and machine learning and artificial intelligence. We'll just set the tone. And then we'll look at the code, and then we'll look at the key takeaways. Okay? So, let's start with the team. I mean, you all know Junior. I mean, who doesn't know Junior? Raise your hand. Okay, so Junior is a mobile engineer at Credit Suisse. He's the president of the Swiss Mobile Developers Association, and he's the key driving force behind this conference for the past 3 years. Okay, he's the heart and soul. And that's me. I'm a mobile architect at Cognizant. I mean, that's about it. So, let's look at the inspiration behind all of this. Go.
Yeah.
Yeah, there's no sound.
Unfortunately, we are without sound.
Yeah, I mean, the sound is the most important thing in this. Okay. Unfortunately, I mean, you all know the music, I trust. And, that's how things start. I mean, you start talking about it, and it's cool, and let's do this, and let's do that. And, of course, hard reality hits you. But I'll let Junior talk about the hardware at this point. So he'll take over and talk about and take us through the hardware and what was actually done with this poor radio-controlled car that we should have kept as it was.
Yes. Yeah. We started with actually buying an RC car. We got rid of the controller. My past, I studied electronics, so I'm a little bit happy to just play with plain electronics, resistors, transistors, and things like that. I studied it, so I told myself, you can actually do that. So we removed that, and we replaced it with a Wi-Fi and a phone. So we're going to actually use a camera on the car, and then stream that from the car to our controller on the car, back to the phone with artificial intelligence, and then the artificial intelligence on the phone controls the car. So some projects that you maybe know from the internet, they does that, but they use like a full computer. But our idea was, can we actually do this with a phone? Can a phone really take over and like do at least line keeping with a car? So we said, let's try with a small one, of course, not with a full one because it's not allowed. You require a lot of license for that. So we started with a small prototype. And of course, when you start with this, the problems are pretty much immediate. So the first attempt, I tried to use an Onion Omega 2. I don't know how many of you have ever heard of this small, kind of similar to Raspberry Pi controller. But unfortunately, it's, as you can see, it's not very powerful. On our test, we used the Omega 2 Plus, so the best one that you can get. It's pretty cheap, it costs like less than $5. And we try with that. So let's see if we can actually do this. But 128 megabytes of RAM sounds too little already. So, and the camera quality was not so great, unfortunately. And the biggest problem is that it went in memory starvation immediately after a couple of seconds. It was like, after 10 seconds of streaming, it was already dying. So let's try something else. And I started to scout. So everybody's talking about the Raspberry Pi. And the Raspberry Pi has this nice small hardware version, which is called a Raspberry Pi Zero, which seems way better. More than 500 megabytes of RAM, 1 gigahertz of CPU, and streaming was amazing. So even the GPIO with some tweaks were good enough to control servers and control a motor. So the second attempt was actually good. And here is the initial setup. And it was very small. I tried to make everything actually working fine with voltage. And I used a back, which basically takes the 7.2 volts from the original battery of the car and transform it on 5 volts for the Raspberry Pi. But the big problem is that RC batteries are crazy. Some of them can give you 80 amperes. This one gives only 40, only. And I'm saying only because did I actually mention that RC batteries are really crazy? Yes, because any problem with the back can actually fry your Raspberry Pi. And guess what happened on Sunday? 3 days ago? Yes, it actually fried our Raspberry Pi. And then we had to find a new Raspberry Pi, which is the full size, to replace it. Then we tried with the camera that was already mounted on the first place. That one was fried as well. So no signal from the camera. Everything was basically dead. We started from scratch. And then, fortunately for us, servers were fine. The motor, the control of the motor was fine. But everything else was just fried. So we started from scratch. But fortunately, today, we completed the complete reset up of the thing, and especially thanks for Patrick that brought us a camera to replace the original one. We were back on track. So I finished the hardware, I completed the whole hardware, and George took over for what it was, the model and the artificial intelligence part.
OK, let's take a stab at neural networks, like I perceive them. But let's talk a little bit about artificial intelligence. I like to go through history in my presentation and touch upon points that I believe are important, because I really profoundly believe that we need to have a sense of understanding of where this technology comes and where this technology is going. So I'm going to take like a small detour, very quick one. I think you're going to like it at the end if you hate it right now. But I mean, it all started in the 14th century, in case you don't know it. Ramon Llull was the first one who came up with the idea. He wanted to create a machine to perform operations in reasoning and not operations in numbers. And his idea of a machine was a machine to convert Muslims to Christians. So it was a big thing back then. He thought he could do it. I mean, I don't think it really worked. But anyway, that inspired, in turn, Gottfried Leibniz in the 19th century, excuse my German, who actually built a machine to perform operations in concepts and not in numbers. And then, of course, we come to 1939, the brink of World War II, with the birth of the computers by Turing. And we have the church-Turing thesis, or the Turing thesis, or the church thesis. I mean, it depends on whose side you're on about this debate, because they came to the same thesis at the same time, that machines can perform any formal reasoning. That's the thesis. But the real first work on artificial intelligence, the first real paper was in 1943 by McCulloch and Pritz. And they talked about a Turing artificial neural network, which is the basis, is the theory behind today's neural networks. Okay? This is where it started. It started in 1943. And then, of course, I mean, we had in Dartmouth College in 1956, we had the birth of the AI field. Then the Department of Justice in the 1960s said, OK, that's cool. Let's build some weapons around this. It didn't really work. Computers were too slow, and they could only play chess, and not even chess, just checkers, I think, back then. But then in the 1990s, with the increase of the computational power, we reached that dark day in 1997, where Kasparov finally lost to Deep Blue by IBM. And the whole idea behind the theory back then was that expert systems dominated. I mean, this is what Deep Blue was. I mean, they coded the rules into the machine, and then they thought if the machine was powerful enough, it could predict the moves in a very efficient way that it could beat Kasparov. So it was a thing about computational power, right? So just put ifs and elses, brute force artificial intelligence, code it, and make it think. But, I mean, that wasn't really working. In the 1980s, machine learning was created. It was obscure back in the 1990s. Okay? People were trying to get Deep Blue to beat Kasparov. So we had deep learning, big data, faster computers, perception advances. And, I mean, IBM, who did Deep Blue, managed to create Watson and win Jeopardy in 2011. And reportedly in 2015, Google had 2,700 AI projects on the site, and that is why we all know, probably, that in 2016, Lee Sedol lost in the game of Go. Yeah, that nothing to do with Lee Sedol. Okay, so, but it lost. I mean, it was I think it was a neural network, whatever. It was machine learning, but the thing is that it learned out of 100,000 games. That's a very important detail. Please keep it. So they gave it the rules. They gave it 100,000 games. It learned how to play, and then it beat Lee Sedol. Now, things get a little bit weird back in July, because Elon Musk said that AI is a fundamental risk to the existence of civilization, to which Elon Musk replied that this is pretty irresponsible to say. And then Elon tweeted that, I talked to Mark about it. He has no idea what he's talking about. So as we all know now, Mark didn't have any idea about almost anything in Facebook. And I guess that is why Elon Musk deleted the Facebook pages. Now you see why he deleted the Facebook pages of hashtag delete Facebook, of SpaceX and Tesla. I mean, it goes back to this, right? This thing about AI, because Elon Musk really believes it's like dangerous. And he also co-signed this letter to the United Nations to stop the arms race with intelligent weapons. Okay. And then Putin said in September that whoever rules in AI will rule the world. Okay, hands off. When Putin comes into play, just you stand back, right? So this is a thing now. We're talking about United Nations. We talk about Elon Musk, Mark Zuckerberg arguing about weapons and AI. We have the UN trying to prevent this in the UN, and then Putin says that. And to make matters worse, AlphaGo 0, which is the evolution of AlphaGo, learned to play Go on its own. On its own. They gave it the rules. They gave it the neural network. It learned on its own, and then it beat that machine 100-0. Straight up, 100-0. Can you imagine doing that? So, and reportedly, AlphaGo 0 found new openings to the game that humans never had thought about. And it played in such unconventional ways that it was crazy. So this is where we are with AI. Okay, enough with the trivia. Let's talk about neural networks quickly. You probably know they are inspired by biological neural networks. What are they? I mean, I don't want to say a bunch of equations, but just a bunch of equations, right? So it's a construct. It's an algorithmic construct, right? And this algorithmic construct has layers. And these layers have neurons. And these layers talk to each other, but only in a forward-facing manner. It's not like the human brains, where our neurons talk to each other. So it kind of looks like this. So this is the human. These are the neural networks of the human. Everything talks to everything else. But in the case of an artificial neural network, it only goes forward. So one layer will talk to another layer. Not all layers will talk to all the other layers, and we'll see that in a second. So we're going to talk about convolutional neural networks. Okay. Convolution is the best way to analyze images right now in a non-literal way. The advantage is that it can identify partial pieces of information, so a part of an apple, a part of a cat, so that's what makes it interesting. And it's one of the most popular interesting techniques when you're trying to tell apart cats, dogs, and fruit. So we're going to give a simple example, and today it's going to be about fruits, so it's not going to be about animals. Okay, what do? We feed the images into the network. The network breaks down the images, it transforms the images to data, and then it starts processing the data by breaking them down into components. And these components then are put together in abstract concepts. This is the convolution, okay? And then they are combined further and further. And at the end of the neural network, the network makes a prediction. It says, I think this picture is a cat. And then it checks to see, is it really a cat? If it isn't a cat, it goes back and it corrects itself. I mean, it seems kind of magic, but it's not. It's purely the mathematics behind it. But that's how it works through backpropagation. The neural network learns on its own like a child. Okay? And this is done over and over again until it learns. So this is how it looks like in abstract. Right? So these are our layers consisting of network of neurons. This is only forward, and each layer is responsible, in this case, for texture, color, shape, size. And at the end, it gives probability of what it thinks this is. Okay? So this is my basic understanding of neural networks. Okay? So enough. Let's go into the code. How did we do this? We use Python's and R's Anaconda distribution. Who knows Anaconda in here? Okay, handful of people. This rocks. Anaconda is, I personally love it. We used Conda for packaging management. We use Python as the programming language. As I said, we're not data scientists, so no R. We use Jupyter as our computing environment. Who knows Jupyter notebooks? Okay, cool.
They're pretty similar to playgrounds for Xcode. If you know Xcode,
yeah.
It's very similar. They are very interactive, and they show the output immediately. And it's very awesome to start with that.
And of course, we used Keras on TensorFlow. What else, right? But we did that on an EC2 instance on the cloud running Ubuntu. Okay? So the idea was, I have nothing. I have no idea. What should I do? My computer is old. It's slow. What should I do? Okay? Fire up an EC2 instance with Ubuntu. Use Anaconda and Conda. Install all of this and start playing around. Okay? And at the end, of course, there's CoreML driving the car in the phone. So, really, version nightmares with CoreML. CoreML doesn't really work with everything. So finding the right combination to make it work, tends to be a nightmare. And this is what we came down. Of course, it's Python 2.7. It's not Python 3. And then it's TensorFlow 1.30 and Keras 2.08 with CoreML. It's the latest version of CoreML. So that was a little bit of a snag. It wasn't. Imagine training the model, doing everything, and then you try to convert it to CoreML, and then it's just like, oh, no, I can't do that. Try. But that's where we're getting to. So now, talk is cheap. Enough is enough. I'll show you the code. And I'm not going to show the iOS code. OK, so first of all, the cool thing about the Jupyter Notebook is that if I can find it, what the hell? OK, we're training in the last minute. OK. So the cool thing is that that's it. So you have your notebooks. These are just text files. And you have your code there, and you execute it just like a playground. OK, that's what Junior said. So the advantage is that with Anaconda and Conda, you create environments. So I can have different environments with different versions installed, and then I can try this notebook in this environment. OK? So first of all, I'm going to execute this line by line. So you're going to see the training on the spot. OK, so we import the libraries. we import our data set, which in this case consists of 3,700 images. I mean, it's a pretty low number, but keep in mind that the whole thing broke down, so we had to retrain it today. So this, I'm going to just run the code. I'm going to import the steering angles, and I'm going to import the images. So what we have recorded from the phone directly is driving the car through the lanes, and what was the steering angle at that given time. Okay? So we're waiting for it to execute. It executed. So let's print it. So, and I just wanted to show you that what's in this arrays is not the images, right? It's a data representation. This is actually the first record. So this is the image, okay? So it's black and white, if you can't see it. And it's just a data representation of the image, okay? You want to say something?
No, the reason that we switched from colors to black and white, it's because if you see the image here, if you stop here, you see clearly the lines. So the contrast of the white tape with the mocap, it's so strong that it makes it easy. Otherwise, with colors, you're going to get much more information. You're going to need much, much more images to train your model. And a good actually approach to this is actually to use that. Some real autopilots are actually doing that in some part of their code. Of course, they're not running like these simple models, but this is a point of start, and this is actually something that really helps a lot. We tried with the color here, and the results were absolutely bad, but in black and white, they were really good, and you're going to see at the end.
Mm-hmm. So, exactly. So what you're seeing is we're taking this data, and we're putting it to grayscale. So this is literally the grayscale of the image. This is what our array, okay? So, and of course, as good machine learning aficionados, I mean, we have to follow procedure. We need to pre-process our data. I mean, data scientists spend 80% of their time in, fixing up data. So we're going to shuffle the data, right? So in is the commands, out is the result. We're going to split the data into 3. We have the training data set to train the model, the validation data then to prevent overfitting, okay, to prevent bias, and then the test data to measure the accuracy of the model at the end. Okay. So we split it up into 3 arrays of angles and 3 arrays of images, and then we augment the training data by inverting the images and flipping the steering angles as well. Additional techniques can be used actually to do that, like artificially adding noise to the data, cropping it, adding hue. I mean, you will find tons of articles on how to do this. We didn't. We just doubled the data. Yeah. Okay. And it's now time to create our neural network. We import Keras, and we come to convolution. Okay, what did we just do? This is our input, which is an image, black and white. That is why it is 100 by 160 by 1. If it was RGB, that would be 3. Okay? This is the dimensions. This is image in. And these are our layers that I discussed earlier. Here we have 5 convolution layers. So we're breaking up the image here, parts of the images. Remember, convolution is very good to identify parts of the image. Then we use a flattening layer between the convolution layers and the connected layers. And then we put 2 connected layers after that. So that's like 5, 6, 7, 8. And our output is the angle. Okay? We can start discussing about convolution and flattening and connected and max pooling and all of this, but I'm going to spare you. We're not going to do that.
Well, technically, you can actually make a single talk of 40 minutes for each of these.
Yeah. I mean, it's
single line of code, because they are very complicated. There is a lot behind it, but it's out of scope to go.
Yeah. And you really need to know what you're doing, right? So why 5 or not 2, and why we have here 5 by 5, and what is max pooling, and why do we have 2 connected layers, and what is the difference between the 2 connected layers, and why are we flattening why do we have this flattening layer between the convolution layers and the connected layers? And we can go on and on and on. But the thing is that images go in, and steering wheels come out, steering angles. Keep in mind, our model has no idea about the steering angles. What the model knows is that he's going to get a black and white image, and he needs to come out with an int at the end. That's it. He comes out with an int. he has no idea what this int is supposed to be. So when it starts, it's just guessing. But it is guessing, right? So this, now we're printing the model here, right? So I just printed it. So 1, 2, in, 1, 2, 3, 4, 5, 6, 7, 8, with the dropouts, okay? And then angle out, okay? So now, here we're telling it where to write the file, and we have some callbacks. And we say, okay, save it if it is better than the previous one. And if you try to train for 5 times in a row and it's not getting better, just stop. I mean, we cannot do any better, right? So just stop. So this is what we're doing here. We're just telling it where to save the file. And then we're telling it to actually save it if it's better and to keep trying, okay? And here is the training. This is where we're passing the training data, the batch size, the epochs. This is how many times we're going to train this. The validation data, remember, for overfitting, right? So this is where it checks if this is correct. What it's doing is correct, right? No, this is for overfitting. I'm sorry, validation is for overfitting, okay? So we're not going to train this 15 times now. We're going to train it like 5 or like 4. But I'm jumping ahead. This is the accuracy prediction we got. Oh, right. What did I just do? I went back. Sorry. Okay. So blue is the expected result, and orange is the result that the network is giving. Okay? So we did a good job at the end in training this. And keep this in mind, and let's not train it, because we trained it like for 15 times. But let's train it for 4 times, and let's see what comes out of it. So it started training, luckily for me. So this is now, it's going through the samples, and it's validating on 75 of them. So it's trying to see, it's going to be finished in 1 second. This is running on EC2. This is a very powerful machine. That's why it's going so fast, and the images are small. And this, at the end, it's telling us how accurate it was. So, I mean, so it started from infinity, and it went to 85.4 loss. So this, it did not improve, or did it improve? Yeah, it improved, so it keeps trying. So it, as you can see, the validation loss is going down, so it's really getting better. Okay, every time it tries, it's getting better and better in predicting. At the beginning is random, as I said, but every time it's getting better because of the back propagation, because it goes back. These fantastic mathematics in TensorFlow are going back and fixing it. Yeah.
What it basically does is just minimizing the error. A good example, if you want to come down from a mountain and it's completely dark, and then the only thing that you have is a small light, and the only thing that you can actually do is going step by step and going down, but at some point, maybe you are in a wrong position and you are going up again. So what you do, you come back, and then you start on the lowest part from the mountain you were. And then you go, and the only thing that you can actually do is step by step. You can only see 1 step ahead of you. And this is what actually is happening. And then it goes on and goes on, and the model, the process that this is, the Keras and TensorFlow are doing is actually minimizing that. And everything is based on metrics and complex mathematics. But at the end, if you check what it's behind this, it's not simple itself, but it's not that complicated to understand and to code by yourself.
So, yes?
So the model has no idea what it's doing?
No.
At the beginning, no.
So then this knowledge can be used for something completely else than that?
No, because at the end, it is going to test against the real data. So when it finishes training, it says, OK, I predict that I should turn left. And then it checks, oh, it's wrong. It should have been right. Because we are feeding it with the right answers. We're giving it the right answers. And it checks itself at the end, and then it goes back and back propagates and fixes and adjusts this. This is all mathematics under the hood, complicated mathematics that thankfully more brilliant people than I am have done it. So, but the cool thing is that you don't have to look under the hood, right? You need to understand what the layers are doing, and then try and try and try again and groom your data and read. I mean, and that's what we wanted to showcase. As I said, we're not data scientists, right? But this knowledge right now, it is so accessible that it's crazy. It's at the fingertips of everyone, right? You can just fire up an EC, you can go outside right now, fire up an EC2 instance, take this and run it. Just like that. No overhead. No posts, no nothing.
Let's see the result. Let's see the result.
Yeah, okay, come on.
Let's see it. I'm excited now.
Yeah, I mean,
come on.
It's going to be worse.
Yeah, it's going to be definitely worse. But
so we're looking at the learned relationship. So how well did it learn? But look at what will happen to the prediction accuracy as soon as we hit this. So I'm going to hit it now. Look at it.
Oh, yeah.
So you see. So this is really not, it totally missing the spikes. It can't go even straight. Right, so it doesn't know how to go because this is the first attempts. It only tried 4 times. We tried 15 times. We could have tried 30 times. You know, but remember that if it doesn't improve, it stops. Right? So this tried only 4 times to learn, and it didn't learn well. So we should train it more. Okay? Okay, and then at the end, you know, it's like we could have converted this to anything. Here we just, I mean, we did. We're not going to use this, but we converted it to CoreML. That's it. And what is so cool about Jupyter is that this is the file I just created. You click on it. It's running on the EC2 instance, and I just download it. That's it. And it's in my it's in my Mac. I can drag and drop it. I can build and run my app. Done. Done. Simply done.
So we were using CoreML, but you can actually use TensorFlow Lite and run it on iOS as well, or Android if you want.
Exactly. So you can take this code, and just take out the last cell, and do whatever you want with it. And that's it. Okay. So this is how it looked. And this is how the training, and this was the, I mean, what we really wanted to showcase. And we're not going to go into the iOS code. I mean, at the end, I mean, we all know how to program an iOS. Where's the presentation? Oh, okay. So, key takeaways. Do we have sound after all?
I don't think so.
Ah, it's a pity.
Let's try.
Let me try to, yeah.
Let's try. Plug it.
Because, really?
Yeah.
Okay. What we would have done differently, and I cannot stress this enough, do not fry the Raspberry Pi the day before. I mean,
that's actually a good advice.
I mean,
maybe have something prepared in case of disaster. Disaster recovery plan is always good, especially with hardware like Raspberry Pi, where like a fraction of voltage more just fries it, and it's.
I mean, in retrospect, it was the bad call. It was a really bad call not to do this. I mean, not to try to feed off the battery of the radio control car. We should have gone with a separate power source. And our friend and colleague Luca, I mean, he was so excited with our pain that he put together a video of our pain the past days. Okay, so. But really, there's no sound. This is so annoying. Because he did such a good job with the sound. I mean, I don't care about the kit video, but no. I mean, look at this. Is just, why is this getting an X here? I mean, Luca, this is for you, man, just for you to hear how good your video was. No, it's just refusing to do that.
I know what the problem is.
You know? Oh, good. Fix it then.
May I?
Of course. Go crazy.
Yes.
Yeah, probably. So real life sound prefaces decoding stuff by Junior Bondolani himself. This is so cool.
Why it's trying to use this?
Keep trying. We will avoid questions at the end.
No.
No, that's okay.
We have, unfortunately, no sounds for some reasons.
Maybe plug and unplug the HDMI and then the sound. Ah, okay. Luckily, this is a Mac, so the speakers are good. Okay. Thanks, Luca. Despair in Junior's eyes.